So, welcome back. In this particular lecture, I will discuss that the sliding wear of alumina, that is one of the brittle ceramic. In the last lecture, I have shown you the some of the very fascinating results, that how the sliding wear of the metals they vary with the sliding environment. For example, when you do the same sliding test, identical sliding test in room temperature, and when you do similar identical tests at liquid nitrogen environment, how does the sliding wear coefficient of friction and sliding wear resistance and sliding wear behavior changes. Now, in next 30 minutes or so, what I'll walk through the specific research results that we have obtained a few years ago when we have conducted the sliding wear tests on self-melted alumina. So, fundamental questions that are to be addressed is that whether so we are talking about sliding wear alumina. So, fundamental questions that are to be addressed is that whether liquid nitrogen can serve as a lubricant or coolant in reducing coefficient of friction. Second one, how does the material removal process occur? So, in case of self-melted alumina, the question of particular interest is that what is the genesis of fracture, because alumina is known as a model ceramic. So, essentially the alumina is expected to undergo brittle fracture in these cryogenic sliding conditions. But the question is that how this cryogenic wear of alumina takes place in liquid nitrogen environment, and how does the fracture or deformation take place during cryo sliding, and how is it different from pure mechanical fracture. So, what is the sliding test conditions that we have used? Here load is around 2 to 15 Newton, sliding speed is somewhere around 2 to 7.5 meter per second, time is up to 600 second, and maximum Hertzian stress is somewhere around 0.57 to 1.1 gigapascal. So, this is the sintered microstructure of alumina, alpha alumina, and this is a scanning electron scanning electron micrograph. So, one is the flat and one is the ball. So, this is essentially the ball and this is essentially the flat microstructure. So, you can see that this is the large tabular grains and these are fairly coarser grains, right. But when you see that there are also bunch of smaller grains or finer grains are also there. So, typical grain size is somewhere under 1 to 3 micron. So, we have done these experiments at liquid nitrogen temperature, and this is the load that we have used 2 to 10 Newton. Now, as far as the frictional behavior is concerned, this particular self-melted alumina shows quite an interesting characteristic. For example, at 2 Newton load, at low load, this friction goes through a transition. Okay. At 5 Newton load, you can see that the red one, it is also somewhere in the middle, and the green one is 10 Newton load. So, it goes through very high value up to 0.3, 0.4 up in the first 3 minutes or up to within the first 3 minutes, and in the next 7 minutes the friction drops and frictional coefficient goes to around 0.15 or somewhere in the window of 0.1 to 0.2. So, this is the window of 0.1 to 0.1 to 0.2, that is how the COF changes. And if you look at these wear surfaces, and if you then you can see there are extremely finer debris particles, and these finer debris particles essentially are the alumina wear debris particles. So, what happens during sliding wear at high speed conditions? The sliding wear at high speed conditions, these alumina grains, they are crushed into finer debris particles, and as a result these debris particles they essentially lead to three body wear situation. So, this is one of the things that is fairly important for you to recognize, that in case of self-melted ceramic, it is the three body wear that can potentially take place, and that can lower the coefficient of friction during as the sliding progresses. Now, the question is, what causes the reduction in the friction coefficient? So, under high sliding speed contact temperature shoots up, and that leads to evaporation of liquid nitrogen. If the liquid nitrogen evaporates at the sliding surfaces, that can expose the matting couples to room temperature conditions, or not the liquid nitrogen, but little bit higher temperature. In case of alumina, phonon-phonon interaction can take place at the cryogenic temperature, and that essentially leads to thermal conductivity, and this thermal conductivity can proportional to 1 by T, and this is in this particular case K thermal conductivity at 77 Kelvin is somehow around 10 times the thermal conductivity what people can measure at room temperature. And then third point, I have already explained that wear debris has a dual effect. So, what is retained, what is therefore very apparent, that high thermal conductivity alumina at room temperature and continuous flushing by liquid nitrogen leads to more intense heat dissipation from the contact zone, and this can explain the reduction in the friction coefficient. This is a schematic and cartoon image. What it shows, that this is the typical asperity from the flat and from the ball. At high sliding speed, you have seen that there is wear debris formation, and this wear debris can be crushed further, leading to smaller particles here, which are trapped in between the two fast bodies, and this takes place under pressure, and this contact pressure, this is the contact diameter what you know, and this is the contact pressure P is equal to W by pi a square. Now, as far as the wear resistance is concerned, if you see that wear depth, it typically wear depth increases with increase in the load if you go from 2 to 10 Newton. The similar trend like linear increase with load has been also observed in specific wear rate. Now, this specific wear rate, their order of magnitude is more important for us, and this order of magnitude is 10 to the power minus 5 millimeter cube per Newton meter. So, this is typically for ceramics, it varies around 10 to the power minus 6 millimeter cube per Newton meter at unlubricated room temperature sliding conditions for most of the ceramics. There can be an exception to that. But what you have noticed here in case of alumina, at liquid nitrogen temperature, cryogenic temperature, this wear is little high. It is like 1 order of magnitude higher compared to what is typically reported for ceramics at room temperature sliding conditions. Now, if you look at this wear depth or 2D surface profile, we do not see very large wear depth. This wear depth is typically limited to 5 to 6 micron depth, and 5 to 6 micron depth, also this wear depth is also observed in case of 2 to 10 Newton and 5 Newton load. Now, laser surface profilometer, that is a standard technique that we used for several other materials, and also we have used here these materials. So, you have a track where you can measure the track width and also the track depth at different locations, and from there you can precisely determine what is the wear volume of the wear track. So, all this measurement takes lot of time, but this gives you much more reliable results. Now, as far as the phase stability is concerned, so this is the unknown, this is the lower one is the unknown surfaces, and this is the cryogenic wear surfaces. So, what you notice that there is not much difference in terms of the XRD patterns of different phases. These are all alpha alumina, and these alpha alumina, all the characteristic peaks are present with similar intensity on both own and unknown surface. Now, these are some of the fascinating microstructures. More you will see when I will discuss about this zirconia, sliding wear of zirconia. So, what you see, there are typically there are general observations of the fine debris particles, but more importantly you will see here there are signs of the cleavage steps, okay, and these cleavage steps, and there are faceted grains. These are some of the features which are mostly representative of the brittle fracture in materials like alumina. So, intergranular cracking and fine debris particles, cleavage facet joining two parallel cleavage fractures, planes, these are kind of some of the characteristic features. Now, if you compare now room temperature and cryogenic sliding conditions, as you have seen this particular image before, the cryogenic sliding where there is a deeper groove and also finer debris particles. Those observations we could not make in that after sliding at room temperature. After sliding at room temperature, all the surfaces are very rough, which is quite expected, but we did not see much of these cleavage steps, but except that fact that there is a this roughness of the surface is promoted by some fracture on these wound surfaces with round edges. So, what we can summarize, at room temperature you have plastic flow and fracture, whereas severe brittle fracture is taking place at cryogenic sliding conditions. So, heat dissipation, the contact heat generation as well as heat dissipation, these are one of the physical events that take place during the sliding condition, during the sliding test. So, we have calculated what is approximately that heat dissipated, heat generated per unit area, that is Q, and that is certainly dependent on coefficient of friction, there is a load per unit apparent area and sliding velocity and so on, and here friction heat dissipated is around 96 into 10 to the power 11, that is joules per meter square. So, these are some of the things that is these numbers are quite important. But if you look at the fracture surface energy of alumina for different planes, for example 101 bar 1 or 101 bar 0 or 112 bar 3 or 101 bar 1. So, these at 298 Kelvin it is around 6 joules per meter square. At higher at lower temperature, as you go in the temperature, the fracture surface energy increases. So, as you can see that 101 bar 1 at 77 Kelvin it is 24 joules per meter square at room temperature, whether it is 6 joules per meter square. So, it is 4 times larger. So, therefore, that higher fracture surface energy of alumina is theoretically predicted, but here we are seeing extremely high frictional heat dissipated energy. So, that is taking place in case of the sliding set, in case of cryogenic sliding conditions. So, frictional heat dissipation is certainly energies is much greater than energies of the fracture surface energies. So, what we believe that this particular, for example, if in this way sliding takes place, so there are two ways these cracks can propagate. One is the intergranular fracture and one is the transgranular fracture, like when fracture crack path crosses the grains here. So, if it crosses, if you see in this cartoon that if it goes through this intergranular crack, so this dotted lines essentially indicate this is the potential grain that can be lifted from the wound surface. Now, if you go through specific wear rate, so specific wear rate, if you see that specific wear rate is reduced and then maximum wear depth is increased in this particular case of alumina. Now, we come to that another sliding system again in the cryogenic sliding conditions, and that is the yttria stabilized tetragonal zirconia polycrystals, and this is the yttria stabilized tetragonal zirconia polycrystals. Here we have varied the load at 5 Newton, 10 Newton, 15 Newton, sliding speed is 1.1 meter per second, time is 5 minutes and maximum Hertzian stress is somewhere around 0.9 to 0.7 gigapascal. So, the question that we are going to address is this transformation toughening that I have discussed at length in one of our earlier lectures, the tetragonal to monoclinic zirconia transformation, whether those that characteristic phase transformation takes place in cryogenic wear or not, and how does it influence the wear resistance in this particular case. So, this is the cartoon. The left one essentially indicates that when a crack propagates and you have a tetragonal zirconia retained in the microstructure. Now, tetragonal zirconia, if it is transformed to monoclinic zirconia, and this is the transforming particles, these are the transformed monoclinic zirconia, that leads to compressive stresses on the crack tip, and therefore, it leads to the crack tip closure, leading to higher crack growth resistance. So, the end point is that as a result of the tetragonal to monoclinic phase transformation around the crack tip, one can realize higher fracture toughness in these materials. Other thing is that you have a primary crack tip, right, and this primary crack tip, at the tip of the primary crack, if there is a tetragonal zirconia phase, tetragonal zirconia grain transforms to monoclinic zirconia, it can potentially lead to the micro cracks from the edge of the transformed monoclinic zirconia. This, by causing the micro cracks and by allowing the micro cracks to grow in the microstructure, the driving force for the propagation of the primary crack tip is certainly reduced. What it means that by allowing the micro cracks to grow, essentially you are restricting the primary crack to grow in the microstructure, leading to more fracture toughness. So these are the two things that can happen. So now let us first look at that what is the frictional behavior in this particular case of self-melted zirconia, when zirconia plate or zirconia disc is being slided against zirconia ball. Now at 15 at lower load like 5 Newton load, there is lot of undulation in terms of the friction coefficient. At 10 Newton load, the coefficient of friction is reduced to around 0.5. At 50 Newton load, coefficient of friction is reduced further to less than 0.4. So this is the typical frictional properties, but like alumina, zirconia, the fracture zirconia also the thermal conductivity is proportional to 1 by T. What it means that, but in this particular case, that K of zirconia, like thermal conductivity of zirconia at 77 degree Kelvin is almost similar to of that thermal conductivity zirconia at 298 Kelvin. And low thermal conductivity, typically thermal conductivity of zirconia is around 2 watts per meter per Kelvin. That tends to nullify the effect of cooling, and wear debris particles are also removed from the wound surface. In terms of the wear rate, what we have noticed that if you see that maximum wear depth, it is going, it does not show it, maximum wear depth shows little increase at higher load, but wear rate, if you see, that shows a systematic decrease with increase in the load. And this is the typical 2D profiles at room temperature. The trace of the 2D profiles clearly show that this is very smooth wound surface, and this smooth wound surface is a very characteristic features at sliding test of 10 Newton load at sliding speed of 1.1 meter per second. So this is the typical laser surface profilometer of the traces of this, how this wear track they appear on the wound zirconia disc. Okay, now coming to the discussion on the wear mechanisms of the self-melted zirconia. What you see here in low load of 5 Newton and sliding speed of 1.1 meter per second, this is your sliding directions. So there are cracks there are numerous cracks, and this is that ensemble of cracks, they are located at 90 degree to the sliding directions. And this at load is equal to 10 Newton, you also see there are cracks, and this is the sliding directions, and you can see there are signs of abrasive wear and severe cracking in these materials. Okay. Now on the disc at 50 Newton load, this is the sliding directions, although these cracks started growing parallel to the sliding directions, but they started deviating from the crack path, but this is the longer cracks which grow straight across the sliding track and perpendicular to the sliding directions as well. This is one of the most fascinating microstructure that I have ever seen on the wound ceramic surface, and this is the condition is the load is equal to 15 Newton, sliding speed is equal to 1.1 meter per second. What we call is the fish scale pattern. Now if you take any of the freshwater fish, and if you look at the scale on the surface of the fish, you normally notice these kind of features. You see that these are the scale which is very regularly placed and physically apart, and this particular the fish scale is kind of placed here. This kind of microstructural features we call it as a fish scale pattern. So, essentially what it means that in this particular case these micro cracks they form, they grow preferably at the direction which is perpendicular to the sliding directions here, and then they do not grow to a very large extent simply because of the limited sliding time that we have. It is like 300 seconds, like 5 minutes sliding. So, if you continuously do this sliding, it is expected that this particular fish scale can grow significantly, leading to the leading to the formation of a macro crack which can extend to a much larger length. In contrast to this fish scale pattern and micro cracking patterns on the wound surface, what you notice a completely different scenario when the same tribosystem or same tribocouple are slided at room temperature or ambient temperature. Okay. What you see here, very clear observations of the plastic deformation and groove formation, and this groove formation is very clear here. If you see, this is the sliding direction, and there is a kind of 35 micron width, these typical plastic grooves, and also this and this is that kind of depth is quite high, as you can see, but in here I have given this 2D laser profilometer traces for you to realize from the scale it is 200 micron. So, the depth is around 175 micron. So, 35 micron width and typical, I am talking about typical length scale, and 175 micron is the depth. So, essentially what you notice, what you see, that width and depth is kind of 5 times. So, it is much deeper, this groove formation that is taking place. We did not see any signature of micro cracking, except there are 1 or 2 occasions of the cracking, but while in cryogenic sliding conditions we did notice significant cracking, micro cracking on these wound surfaces. Now, from material science point of view, it is also important for us to analyze that what is the whether the phase transformation of zirconia is taking place during the sliding wear conditions. For that, what we have done, we have taken the sliding track, we have recorded that X-ray diffraction pattern from the unwound surface, that is before the sliding test is over. Then after that, we have focused our X-ray beam on the sliding wear track after the room temperature sliding conditions and also liquid nitrogen sliding conditions. What you notice, there is a very sharp crystalline peak of tetragonal zirconia, no sign of monoclinic zirconia or any other phase. After room temperature sliding conditions, we do see tetragonal zirconia is present here. However, a different observations we have made when we have closely looked at the XRD traces, what we have recorded of the cryogenic sliding conditions. We see signs of orthorhombic zirconia and monoclinic zirconia, but some of the peaks are very critical, very clear signs of this orthorhombic zirconia only. So, what happens, the tetragonal zirconia can undergo phase transformation to orthorhombic zirconia as an intermediate transformation product before it goes to full transformation to monoclinic zirconia. So, what happens in the cryogenic sliding conditions, you are doing this test for 5 minutes. So, you are not allowing the system to undergo full transformation from tetragonal to monoclinic zirconia, and that is quite an interesting observation that we have clearly see at the same time scale when tetragonal zirconia is retained, it does not undergo any phase transformation at room temperature sliding, but under cryogenic sliding conditions on the same samples under identical sliding conditions, tetragonal zirconia undergoes phase transformation to orthorhombic zirconia, and there are also signature of the monoclinic zirconia formation. So, this is the kind of closer notes on the self-melted alumina. We have seen there is significant effect of load and also material removal from both flat and ball by transgranular intragranular mode of fracture. In case of zirconia, it is that high steady state COF of 0.35 to 0.75 has been noticed, and it is experienced at tribological testing at 5 to 15 Newton, and then spalling and microcrack induced damage are the major wear mechanism under the cryogenic sliding conditions. Thank you.